Alrighty, so the next part of our notes is about circular kinematics. And to understand what that is, we really have to make sure we remember what regular old kinematics was. So all this question that we're trying to answer now is we were looking at things that moved at a constant speed in a circle, and now we're going to look at what happens if that it is speeding up also around the circle. So it's not going at a constant speed around the circle. That speed is going to be increasing. So really, there's just a circular version of everything that's linear. So when we look at position in the linear sense, we use the symbol x, and we're talking about meters. And this is describing where something is. In a circle, then we're looking at an angle instead. So instead of saying this went 5 meters, we could say that it went 5 radians. And that's describing where it is around the circle. And we use this symbol right here called theta, and the unit that we use is radians. So all we are doing is replacing position x with angle theta. Same idea with velocity. We use v for velocity, and that's meters per second. And again, that's how many meters are covered in a certain amount of time. So every second, an object will move x number of meters. And for a circle, you already know what angular velocity is. That's omega. And that's describing, for every second, how many radians does this thing go through. So it's measured in radians per second. And you see where I'm probably going with this. Now, acceleration is how much does your velocity change over time. So every second, there's going to be an increase in your velocity. So for example, I could be speeding up 5 meters per second every second in a straight line. But if we're talking about angular acceleration, now notice this is not centripetal acceleration. This is angular acceleration. So this is how much does your angular velocity change every second. So we're looking at radians per second. And that symbol that we have right here that looks like a fish, that's alpha. So that is your angular acceleration. Now, we have equations that relate everything over here on the left, x, v, and a, with time. And we have all those equations that we can describe where something is, how long it took to get there, etc. We can do the same exact thing with circular motion. And the good news is that there is no such thing as rotational time. So time is just time. There's no linear or rotational version of that. It's just time. So there's nothing weird about that one. So that was one of our first equations that we did for velocity, acceleration, and time. Well, if you think back to the last page, all we're doing is rewriting these same exact equations, but in terms of angular velocity, angular acceleration, and the angle. So the equation here on the right is just the angular version of the one on the left. So the one on the left says the final velocity is equal to the initial velocity plus the acceleration times the time. Well, on the right, all it is this is the final angular velocity equals the initial angular velocity plus the angular acceleration times the time. And we can rewrite all of those other equations in terms of the angular version. So when we look at the one with final velocity squared equals initial velocity squared plus the rest of that, it's the same exact pattern with the angular acceleration on the right. So instead of that, we've got final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration times theta, the angle. I know I'm saying angle a lot, and get used to it. So, and then our last one we have is this one, so the really long one. Well, all we're doing is replacing omega with x, theta with x, and omega with v, and alpha with a. So our equation, as far as the template of what the equation looks like, it's exactly the same. It's just the letters are different. I'm going to skip that one and come back to it later. Okay, so the interesting thing that we can do now is we can actually convert from linear to angular. So if we have some angular velocity, let's say this thing is going like 10 radians per second, and we want to know linearly how fast something is moving at a certain radius on that circle. So what we'll have is, let's say we got this as our circle, and I gave some angular velocity of, let's say it's 10, oops, that didn't work, of 10 radians per second, and it has some certain radius here. Well, the radius doesn't really affect the angular velocity at all. All this angular velocity cares about is how many angles does it go through every second. So, but if you think about, let's say this is like a merry-go-round, like that, so it's spinning like this. If you're at different points along the merry-go-round, you're going to feel like you're going different speeds. So what I'm going to show you here is how do we convert from linear to angular, or angular to linear. And this right here, this S, that's what we call the distance. So that's a linear distance. And R is the radius, theta is the angle. So at any angle, we can say like how much that arc length was traced out. So again, here's our circle, and let's say that that right there is the angle we went through. So let's say that was like 3 radians or something, and I want to know what this length here is. So that's our arc length S, and this is how we would find it. You just multiply by the radius. And the pattern follows the same for velocity and acceleration. So if I want a linear velocity and I only know the angular velocity and radius, I just multiply those two together, and that'll give me this. Same thing with the acceleration. And the acceleration linearly would just be radius times angular acceleration. All right, so let's put this concretely in an example. So here's a wheel, bike tire. It has an initial angular velocity of 0, radius of 60 centimeters, and it's going to start spinning. So it's going to be spinning faster and faster and faster as time goes on. So there's going to be an angular acceleration, and it's going to do this for 4 seconds, and it has an acceleration angularly of 4 radians per second every second. And the question that I want to answer is, what would its angular velocity be in 4 seconds? Well, easy enough. We just plug it into that equation, because we know that we have the angular acceleration there, we know the time, and we know the initial angular velocity. So at this point, physics is done, and it's just plugging into an equation and calculating the number. So it'll be going 16 radians per second. All right, well, let's answer another question. How much did it turn? So how many radians did this spin through in this same process? Well, we know that we have a final angular velocity there. We know the time still is still 4 seconds. We know the acceleration, and we know it started from rest. So we can use all of those things to find out what theta final is. And we're going to use that equation because we know that one was 0. The initial, it was at rest before anything happened, and it didn't have any initial angle to start with. So all we're left with is 1/2 alpha squared, or no, 1/2 alpha t squared. So again, this is just a plug and chug at this point, and we plug in all of our numbers, and we find that it turns 32 radians. Okay, a more interesting question, or something that's easier to wrap your head around, is how many times did it spin? How many full rotations did it go through in this time? Well, let's figure this out. Now, you may already know this, but I'll remind you. In terms of relating things like rotations and revolutions, those are just words that say how many times did it spin? How many times did it go in one complete circle? And we know that every one of those rotations or revolutions is equal to 2 pi radians. So one circle, doesn't matter what the radius is, to go around one circle is 2 pi radians. So we had 32 radians. We just have to convert it. And so we're going to divide this by 2 pi. And when you are doing these conversions, a lot of times you're going to get things like revolutions and rotations, and you'll have to convert back and forth between those and radians. And this is how I recommend you do it. I don't recommend just memorizing, oh, I know to divide or I know to multiply. Do this. If you've taken chemistry before, this is nothing new to you. It's just called the dimensional analysis. So all you're trying to do is just cancel out the units you don't want and be left with the ones that you do want. So more of that you'll probably see in class. But anyway, this is, we crank this out and we get 5.1 rotations. So it spun a little more than 5 times, just barely. All right. Let's do another example, but we'll use the same numbers. So we've got the same problem again, but instead of that bike tire just spinning, let's say that we're actually riding that bike. And the question that we were trying to answer here would be, if we know that it accelerates angularly 4 radians per second every second, and it's doing it for 4 seconds, and it starts from rest, what would its final velocity be? Well, all we need to do here is convert our angular velocity into our linear velocity. Since we know the radius of the tire is 0.3, then we know that at the edge of the tire of the bike, or the motion of the bike, is just going to be that radius times velocity. So it's 0.3 times 32. We're going at about 9.6 meters per second at the end of that time. One more thing that I want to do is talk about what RPM means. Because you're going to see this in a couple of word problems, and you may not really know what this means. Well, what it is it's just revolutions per minute. So the tricky part that you'll have to come across figuring out doing is, let's say we have an example of 20 RPM, and I want to know what that is in radians per second so that I can plug it into my equations. Well, this is just going to be 20 revolutions per minute, and then I'm just going to do my dimensional analysis again. So I just need to convert this to radians per second. So 1 revolution or rotation, same thing, it's just one time around, is equal to 2 pi radians. And that gets rid of the revolutions unit. So at this point we have radians per minute. I still want it in radians per second, so let's convert the minutes to seconds. Oops. So 1 minute. This pen is not working too well. So 1 minute is 60 seconds. All right, so that minute cancels with that minute, and then we're left with something radians per second. So I'll go ahead and calculate that out super quick. So we've got 20 times 2 pi, and that divided by 60. Our answer, I'm going to write it on the next page. Actually, I'll just write it right here. So we had about 2.1 radians per second. I know it looks like red, but I meant to write rad. So there you go. That's basically circular kinematics in a nutshell.